to look at a couple of these properties just as far as review. Many of you were comfortable with 1 through 5. The questions came up on 6 and 7. So I'm just going to draw a couple of pictures to help us process that. For 6, if I look at the min-max inequality, it's asking us to compare the min of a function times b minus a to the definite integral to the max of a function times b minus a. So what I'm going to do is I'm going to draw a function on the interval from a to b that has a min value and a max value. There's the max value. There's the min value. Okay there? Okay? Since definite integrals are always an area argument, that area is equal to that integral. Good? The exact area under the curve between a and b is equal to the definite integral. Good? I should use the word net area, but since the function's positive, it's the actual area. Okay? Now, if I were to use, I'll use another different colored marker here, but if I were to use the minimum of function times b minus a and think of it in terms of an area, b minus a is this length, right? And the minimum value of the function is this length. What did I find with this calculation? I found the area of this rectangle, did I not? Make sense if I put it that way? Now, should we all agree that the area of the red rectangle is smaller than the value of the definite integral? Yeah, because whatever this rectangle is, the height of it's the minimum of the function. So it's got to be the smallest, right? Same idea with the max. I'll use a different color here. For the maximum value. Maximum value is up here. This is the height of a rectangle. That rectangle does this. And I think with the color coding that helps. The smallest one is the little rectangle down there. The one in the middle is the actual shaded area under the curve. And the largest part of the inequality is the rectangle that bounds the whole thing. Does that make sense for number 6 a little bit? Okay. For number 7, it asks us to draw, I mean, it doesn't ask us to draw, but it implies that you draw some function f above some function g. They don't need to be the same shape. I just happen to draw them the same shape. Okay? But if the function f of x is greater than or equal to the function g of x, that really, graphically, that means above. Greater than means above. If f is above g, how's the area under f and the area under g related? We can shade it really quick. Area under f, area under g. Which one's bigger? F. So then we throw notation on it and say the area, the net area under f of x is greater than or equal to the net area under g of x. That makes it a little easier when you draw a picture, doesn't it? Okay. Other questions on the properties before I move on? Okay. Here's what I'd like you to do. I'm going to kind of split you into some groups here. One group is going to do A and D. Another group is going to do B and E. And another group is going to do C and D. I think we can do this in about 2 minutes. I want these 2 rows to do A and D. We'll kind of do this spatially. You guys get A and D. Middle 3 rows get B and E. And you guys get C and F. And here's what I'd like you to do. I'd like you to find the value of the integral if you can. And if you can find the value of the integral, I'd like you to connect to which property you're using. You can just identify it by number. I used property number 1, the order of integration. If you flip the order of integration, you make the area negative. Put a negative in front of the area. So identify the property you're using, or if you cannot find the value, I want you to state why. What information do you need or are you not given in order to answer this question? And I'd like to have somebody from your group ready to talk on those 2 talking points in 3 minutes. Go. So we have the answer shown. We decided that D, E, and F Can't be done completely at this point, but we used some notation on f to simplify it just a little bit. Okay, want to take you back. And I know we did this in chapter 1, but I want to talk about even functions and odd functions. How many remember being in a calculus class earlier this year, probably September, where the phrases even function or odd function were used? How many remember? How many were in a calculus class first semester? Excellent, good. We got full participation now. Awesome. You can even go back to pre-calc. Did your pre-calc teachers teach you even and odd functions? Okay. We want to be careful because we don't want to talk about polynomial functions with an even degree or polynomial functions with an odd degree. We want to talk about an even function or an odd function. There's a very specific definition. There's a graphical definition and an algebraic definition. Let's start with an even function. Oh, no, sorry. Let's start with an odd function because that's what's first in your notes. Okay? What is the algebra? Does anybody know the algebraic definition for an odd function? I'll start it. Odd function, f of negative x is equal to, do you remember it now? Awesome, negative f of x. That is the algebraic definition for an odd function. Do you remember the graphical definition for an odd function? What property does a graph have if it is an odd function? Starts with symmetry. But you all were thinking that, weren't you? Symmetry about what? About the origin. I'll draw a basic one. Sine x is an odd function because sine x on the interval, that's upside down, guys. Sine x on the interval from negative pi over 2 to positive pi over 2 looks like this. That's an odd function because it's symmetric about the origin. Okay? Now, from an area standpoint, why does that statement make sense? I'll help you with the picture. Does that make it a little more clear? If the function is odd and the bounds of integration are symmetric, I'm going from negative a to positive a, like negative 10 to positive 10, or negative 2 to positive 2. They have to be the same, but they have to be opposites. The area, the net area is going to be 0. Why? Because anything below is considered negative and anything above is considered positive. Now, extension back to what we just did. If we knew that f or h were odd, which question could we answer now? D, E, or F? D, E, or F? Tell your neighbor. Which one could we answer now? E. If, and this is only true, you can make a note this if you want to, but if h is odd, the value of that definite integral is 0. Because I've got area below and area above, or vice versa, because of the symmetry of an odd function. Cool so far? Okay. Let's look at even. Do you remember the algebraic definition for even? F of negative x is equal to, if it's even, f of negative x is equal to f of x. Symmetry about what? Symmetric about the y-axis. There's an example of an even function. It's a reflection over the y-axis of itself. Okay? Parabolas are good examples. Cosine is another good example. It doesn't have to be a parabola in order to be an even function. Cosine is another good example of an even function. Okay? And this basically tells us if I'm going to integrate from a negative value to a positive value, those values having the same absolute value, I could have shortcutted it, and I don't know how useful this is, but you could have shortcutted it by just evaluating over the positive portion and doubling it. If I look at the cosine curve, that makes sense, doesn't it? There's the cosine curve. If I found this area and I doubled it, I'd get the whole thing, wouldn't I? Okay. Which one does that help us solve? D, E, or F? Actually, it's not going to be E. D or F? D. And some of you, a couple of your groups were talking about this already. If the function, if f was an even function, f is even, and I know the integral from -1 to 1. I know the integral from -1 to 1. If I went 0 to 1, I should have half the area, shouldn't I? 2.5. If the function's even, it's got symmetry. Okay? That's a 2.5. If you know the function. If you know the function was even, I'll write it better over here, 2.5. If you knew that function was even, then the area between 0 and 1 should be half the area between -1 and 1. Cool? All right. Why are these useful? All these are useful for, guys, is for time-saving measures. It prevents you at times from having to substitute negative values into an antiderivative. Substituting negative values is painful, isn't it? It's not that painful. But what does it cause? Substituting negative values causes potential sign errors, right? So this could save us a little bit of trouble. So using the symmetry idea, let's evaluate these three. I'll go through them kind of quickly, but jot down what we're doing in your notes, and then we'll get to one more big topic for the day. All right, so let's look at this function, -3x squared. Even, odd, or neither? Even. Why is it even? Okay, x squared is a good argument, but not all x squareds are even functions, because if I had an x squared function that looked like that, that's not an even function. What about it? It hasn't been shifted. That's the key. It hasn't been moved left or right, most importantly. It can go up and down and still be even, but it hasn't moved left or right. So it's an even function. What might help us here? We can now state, because it is even, we can do this integral as twice the integral from 0 to 2 of -3x squared dx. Is this going to save us a ton of time? No, because we're still going to use the fundamental theorem of calculus version 1, but it prevents us from having to plug in a negative value into an antiderivative. I think that's a little bit easier. Also, when we did fundamental theorem version 1, I also told you that if you have a boundary of 0, it's always going to be easier to evaluate. Okay? What's the antiderivative of -3x squared? -x cubed, right? Evaluate from 0 to 2, and then take that value and double it. Do I need a plus c? Good question. If I'm doing a definite integral, if I evaluated at b and I evaluated at a, the c is going to be in both, so the c's would subtract out. So I don't need the c's for a definite integral. Okay? So this then becomes a function evaluated at 2, which ends up being -2 cubed, do it that way, minus -0 cubed. You like that 0? Say yes. Zeros are good, right? So this ends up being, this portion's 0. This is -8, right? So the value of the integral we wanted originally is -16. Okay? Could you have done fundamental theorem without the doubling process and put a -2 down here? Yep. Do you see that the 0 is a little easier? It's a time-saving tip. It's not going to change your world, but it's a time-saving tip. Okay? Part B. Cosine x, we referred to it earlier. Even, odd, or neither? Even. I like this one a lot, guys. Because I consider myself pretty decent at trig. I'm not outstanding at trig, but I freak out at trig when angles get negative, don't you? Don't like negative angles. I just don't. I hate them. They make me angry. So here's what I can do. If I know it's even, I can double the integral from 0 to pi over 2 of cos x dx. Again, not earth-shattering. Could you plug in negative pi over 2 to the antiderivative of cos? Absolutely. But I think this is a time-saving trick. Okay? Antiderivative of cos? Sine x, right? Do I need a negative on it? What's the derivative of sine? Cos. Do I need a negative? No need for a negative. I'm going to evaluate from 0 to pi over 2, and then I'm going to double it. So this is sine pi over 2 minus sine 0, all doubled. Don't we love the 0, guys? What's sine 0? Sine 0 is 0 sine pi over 2. 1. So that value is 2. Okay? Be careful when you get to part C. I'll pause for just a moment to get you caught up. Take a look at part C. Algebraically, try to determine whether it's even or odd or neither. What are you hoping for, by the way? Even, odd, or neither? Odd, because it'd be easier, wouldn't it? Symmetric bounds of integration on an odd function, you'd get 0. Wouldn't it be awesome if that function was odd? Because the whole thing would just be 0, wouldn't it? Is it odd? Shoot. It's not odd. Is it? Did you try it? Let's try it quickly. Let's go f of negative x. That's the algebraic definition. That's negative x to the 4th minus 3 times negative x to the 3rd. Negative x times negative x times negative x times negative x, that's just the same as x to the 4th, isn't it? But then when I've got a negative to an odd exponent, this ends up being plus 3x to the 3rd. Is it odd, even, or neither? Say neither. It's neither. But part of it's even, isn't it? Which part's even? The x to the 4th part's even. Is part of it odd? The second part's odd. So we can use a property we learned earlier today. Again, could you do this the long way? Absolutely. But knowing the property can shorten up your work here. Let's do this. Let's do negative 2 to 2 of x to the 4th dx plus negative 2 to 2 of negative 3x cubed dx. We just cut our work in half, guys. Why did we cut our work in half? Second one is odd, so it's 0. The value of this integral right here is 0. Why? Because it's an odd function over symmetric bounds over the origin. Make sense? A little bit? Question? Yes, you could have done, yes, good question. You could have written this as, yes, you could have done the subtraction in the middle as well. Yep, very good. Okay, so now what do we need to do? We can cut our work in half again, kind of. We can just go ahead and integrate from 0 to 2 of x to the 4th dx and double it, can't we? Because x to the 4th is even. So this is x to the 5th over 5, evaluated from 0 to 2. Love evaluating definite integrals, starting at 0, guys. What's 2 to the 5th? 2, 4, 8, 16, 32, right? What's 0 to the 5th? 0 to the 5th is 0, so it's 32 fifths times 2, aka 64 over 5. Okay? Are the properties going to change your world? Is knowing even and odd going to change your world? No. But they're nice little shortcuts if you can get to them. Okay? One more concept. Can you do it? Okay. Average value of a function. I'm going to show you the long way. I'm going to show you the derivation of this formula. Derivations are cool, right? Are derivations high stakes in the long run? No. But I want you to see this, okay? Let's talk about the average value of a function. Let's say I had all of your heights in meters. How can I find the average of them? Add them up and divide by how many there are. If there's 30 of you, I'd add up your heights, divide by 30, and then we find your average height, okay? So we have a sense of how to find the average of a set of numbers. You've been doing it for years, right? Doing it since like 4th grade. You do them in your sleep, okay? But what if we had an infinite set of numbers? Okay, and before we go to an infinite set of numbers, let's do it in general with n numbers. And I'm going to do it graphically. Are you ready for this? Okay, I'm going to draw a picture. This is the derivation of it. Now, could a person memorize this formula and be happy for the rest of their life? Absolutely. A person could not take this class and be happy for the rest of their life. That's also true. Okay, but I'm gonna do a derivation for you because it's a nice connection to what we've done. Let's say I have n pieces of data. The function always looks like this, doesn't it? Let's say we have n pieces of data between A and B. Okay, I want to tie this in a little bit to rectangles because I think it makes sense that way. Okay, let's say we have n pieces of data, aka n rectangles, because that's really that's really kind of you're adding up function values, you're adding up the heights of rectangles, right? So let's say we have n rectangles. Okay, delta x, back to a couple of weeks ago, delta x then would be the length of the interval divided by n. B minus a divided by n would be delta x. Okay? Hold on to this for a moment. Okay? The average of n values would look like this. The average of n values would be the function evaluated at the first piece of data plus the function evaluated at the second piece of data plus the function evaluated at the third, and so on, right? Divided by n. With me on that? Because the function represents a height value. Maybe person 1 is 1.5 meters tall. Person 2 is 1.8 meters tall. That's kind of tall. What if person 3 is 3 meters tall? Wouldn't that be awesome? 3 meters, that's over 9 feet. That's pretty tall. Okay. We okay with this so far? If I have n pieces of data, I have n function values, I add them together, I divide by n. Good so far? Okay. AKA, shorthanded notation, 1 over n times the sum from I equals 1 to n of f of x sub I. What am I turning that into? Starts with an R. Riemann sum. Oh gosh, guys, this is going to get good. Okay? Some of you are shaking your head in great frustration. Okay? Let's substitute for n. We'll take care of the limit part in a minute. Okay? Let's take care of n. Delta x is b minus a over n. So what is n equal to? Can I say b minus a over delta x? Yeah? Fair? Algebra? Okay? So now I'm going to continue this along, except I'm going to substitute this in. This is 1 divided by b minus a over delta x times the Riemann sum I equals 1 to n f of x sub I. Okay? Got a complex fraction. Right here. I got a divided by a divided by. If I get 2 divided bys, what can I call it? A multiply, right? So this could be written as 1 over b minus a times delta x sum I equals 1 to n f of x sub I. It's coming together, isn't it? You could put the delta x on top. That's a good question. But where do I want the delta x? In order to really make it a Riemann sum, I want the delta x right there. Does that make sense? It's a good question. But I'm going to put the delta x over here. Okay? Good so far? This would give me the average value of n rectangles. But n rectangles just isn't enough, is it? How many rectangles do we want? It'd be great if the number of rectangles approached infinity, wouldn't it? It always is better if we approach infinity, don't you think? So let's just, what do we say if we want the number of rectangles to approach infinity? What command is used? Limit. So now I'm going to go 1 over b minus a times the limit as n approaches infinity of the sum I equals 1 to n f of x sub I delta x. And that should be the average of an infinite number of data points between a and b, shouldn't it? We derived it. But what's that big thing in parentheses next to the 1 over b minus a? That's the definition of a... It's a Riemann sum that we made infinite. It's the definition of a what? Don't look very far away from where you're at right now, guys. Don't look very far from where you're at. What is this thing? That is, by definition, the value of a definite integral, isn't it? We did that last week. Wasn't that fun? Okay? So you can believe in this formula if you'd like, but I think it gets a little more power from the derivation. Okay, you're just done. You're done with me today. You're done. Okay, last idea really quick then. So, it's not a new idea. Let's go through this example and then we'll call it a day. Do this example, we'll call it a day. Find the average value of the function on the interval from 0 to 3. Okay? Average value of the function on the interval from 0 to 3. So to find the average value, we're going to do 1 over 3 minus 0 times the definite integral from 0 to 3 of 4 minus x squared dx. That's our definition of average value. Okay? That's going to be 1/3 times 4 minus x squared is an antiderivative of 4x minus x cubed over 3, right? Evaluated from 0 to 3. We love starting at 0, don't we? Put in 0 to a polynomial, you get 0. So this ends up being 1/3 times the quantity 12 minus 27 thirds. It's 12 minus 9. So 1/3 times 3 is 1. The average value of 4 minus x squared on that interval, we could draw the picture if you want to, on the interval from 0 to 3, the average value of that function is 1. Good? It's not intuitive, but it works, right? Okay, and then the last idea I want to leave you with is the mean value theorem for definite integrals basically says if we find the average value of the function, that value has to be on the function. Of course. That's the mean value theorem for functions, right? It's got to go through its average value. So if you find an average value of 10, the function's got to go through 10 because of the continuity idea. Okay? I am going to give you some average value FRQs that I don't need you to start tonight. We'll probably start class with it tomorrow, but I want to give it to you now.